Stayed around, you had a busy fall break, even though.
Okay,
Yeah, stayed around and did whatever.
Yeah, just chilled around.
Yeah, that's kind of what we did. It was kind of weird because the gymnastics schedule changed a little, but not the whole week. Because like all the boys that are of a certain level had this last week off. And then some of the boys that were of a different level have different weeks off. So it just got crazy. So like we did, it was supposed to be Monday, Wednesday, Friday in the mornings. And then Tuesday, Thursday in the afternoons. But Monday, the other boys weren't available, so Drew went for 3 hours by himself and basically got 3 hour private with the coach. That was exhausting. And then Wednesday was normal, and then Thursday and Friday there was no practice because of the storm.
Oh yeah.
Yeah. Do you know anybody that lives in any of the areas that were?
Yeah. My dad's friend, like his neighbor's tree, fell. His neighbor's tree fell into his property.
Yeah, that's no good.
Thankfully, we had no power outage.
Yeah, we didn't either. There was nothing here, but
my brother's like, when I grow up, I'll have an acre of soul.
I
have no idea what that is.
We have a generator plug-in. So we could put a generator outside, and so we have a central plug-in where we can put it, and then it can run at least portions of the house. But the generator itself isn't good, so we need to like replace that before we get another storm, so. Yeah, we have some good friends, actually, we have 4 groups of friends that live in the area that got hit the hardest up in the mountains. One of them left beforehand and they were fine. Another set of friends were able to by Sunday, they were able to get out of their house.
So what damage did they get?
Well, they posted, he showed pictures of his yard. Shared this morning. It was kind of crazy. So their house is up like on a hill. They kind of want to get to a little hill to, let's see. So this is what it was before it started. Okay.
Oh.
Right? It ended up within 3 feet of their door. Look for their mailbox. Their mailbox?
Yeah.
It was about down here in the road, it was about 20 feet deep because their driveway is way steeper than that actually shows. So the picture doesn't do it justice. So they had about 20 feet of water in their road. And one of them was stuck in the house with the dog. And then I have another friend who lives there in Asheville, and she has a little power because they have some solar panels, but she doesn't have any water and she doesn't have major power, and their cell towers are not doing great. And their entire basement is flooded. Yeah, and then I have one other friend, actually, I need to check and see if they got to her yet.
I think
She's been stuck in her house with her dog and they're out of dog food for days. And it's getting rough.
in my taekwondo, the coach said who got damages, and then there's this kid who got insane damages, his basement was flooded and they had to go they had to stay at the top, and that was
Yeah. It's going to look like this. What's going to give you a really big is that she has any new updates here. Okay. See how your subject pronouns line Yeah, it's gonna be wild for those people to get help. I was just checking in on my friend. Nothing, nothing yet. She can't get home, so. It's not good, man. It's just weird because you move to the mountains, you don't think you're gonna have trouble with a hurricane. Those are coastal problems usually, right? So,
Well, are we gonna learn more about hurricanes in earth science?
yeah, we do a lot in our
Earth
science.
science is basically about Earth.
We do a lot with weather systems in our science, and it's a lot of fun. We actually try to build hurricane-proof house structures and all kinds of things. It's a lot of
Wait,
fun.
are we gonna build real hurricanes?
You build a little model house.
Oh.
Yeah, try to make it so it doesn't blow over when you hit it with a really, really strong fan. It's fun. Yeah, we had one little tiny tuft of hickory tree about this big that landed in the yard, and we were all like, but the river got to probably the highest we've ever seen it. Actually, on Thursday night, Friday night, I don't remember what day it is now. Jason got on the news briefly, well, Jason's video got on the news, because he went down there and filmed video of the river. And then a friend of ours, he shared it to social media, and a friend of ours shared it to, her friend who's a media, news reporter. And then she was like, oh, that's a really great video, it actually did overflow the banks, which doesn't normally happen, so he went down there again and got more video the next day, so we.
Well, I've heard like most of the creeks have gone flooded.
Yeah, a lot of the creeks flooded, so. Hey ladies, what's up?
Wait a second, I think I found a brownie point or something.
Oh, write it down and put it over there.
Okay, 1 second, let me just see. Okay, yes, it is.
There's Lucy.
Hey, why are the papers out?
Oh, did you read it? Did you see the big spider web? You can go look right by the, right near the front window of the house, there's about a 3-foot wide orb. It's amazing. You didn't see it, go peek.
Spider web is real?
You didn't see it? Come here, I'll show you this. It's huge.
Miss Danny? Miss Danny? You know. I don't know where to put this thing. Yeah, I know where to put, into. Yeah, there we go. Did she not put the magic? Yeah. This stuff isn't put down. They have Rico pictures to put in, the hand.
Oh, I need to put down here. Yeah, so Drew did you do your classes and stuff yet? Like your drug test? Yeah, so Drew's done his test, so all you have to do is go to DMV.
Oh, my older brother got it done. I don't know. Brownie point. Brownie point. Mendelea, not Mendelea. Dimitri Mendelea. Yeah. There's no crowd. Yeah. In the booth. Right on time. Wait, Annabelle, did you see the giant spider web?
This is the driveway, and it does not do the giant spider web here.
Did you not see it?
It's been 3 feet. I don't think so.
Okay, come on. I'm gonna show it to you.
It's fine. I think 20 to 25 feet. Only. Everybody okay? Like, they're fine. They couldn't get out. So Jason works in Asheville, so he in Greenville. So he had commuted, and he works at the hospital as a chef. So it's like the whole thing. So he was there, and Bo the dog were at the house. Bo the dog was back. But Jason couldn't get home Saturday night really late. We had to come in through the hills, we had to come in with a bad day. They can turn right out of the driveway, if they live and walk the river, like they walk the dog. our favorite thing is to go to the river park. We do have one friend, she was in Detroit, and loved from the dog. And she's made it. She gave it a in Nashville, but she came home to her and they I was almost out of human food. We were out of dog food. And that was so yeah, I don't know how she's doing. I just texted her this morning, I was like, Laura, okay, with Erin, is Erin? Yeah, I mean, just rough, man. Hello. How was everybody? I showed this to Eunice a minute ago, but I'll show you guys. So we have a really good friend that lives in Asheville. You see the news, right? This crazy hurricane came through there and it caused all kinds of flooding. Yeah. So they live very near the river, okay, that has flooded. Like they walk to the river, they have a dog named Archie and they take Archie to the river all the time. First, this is Archie. Right, he's adorable. That's Archie. Now, their house, they have like a condo style house and it's up high on a hill. And there's about 20 to 25 feet elevation from their front door all the way down to the road. So this picture doesn't do it justice, but like this is how it looks. I love that he put Rocky like a hurricane is the sound, right? This is how it looks normally. That's very far down. That water came within 3 feet of their door. It's like 20, 25 feet deep at the road.
How long?
It was like that for 3 days, but they can get out now. But isn't that crazy?
That's hilarious.
Is their dog okay? Is their dog okay?
Oh, Archie's fine. Yeah, he can't go for his walk at his favorite place, which is down by the river because it's all flooded still. But he'll survive. Yeah.
How are they gonna get groceries?
They don't have groceries. Unfortunately, Jason, one of the guys that lives there, he's a chef and he works for a hospital. Not my Jason, his name's Jason too. They've been friends since kindergarten, Jason and Jason. But anyway, he works in Greenville and he found a route that he can take to and from Greenville to Asheville safely. And he, because he works as the chef at a hospital, he's able to get like some extra water and things. They told him to go ahead and take it. So he can at least take it home for Bo and the dog. So it's a mess. And I got another friend who's apparently got a flooded basement and no power, no water, very little cells. Because the water came up so high, it just came into people's houses. So their whole basement's flooded.
Yeah, probably the glass.
Yeah, and one other friend
They
who
don't have a basement pool.
can't get home and her spouse is there with the dog and they have no more food and no more dog food and they're stuck. So it's a mess. It's a real mess.
Wait, are they gonna live?
I mean, I'm hoping they're gonna be okay, but they haven't been able to get any help to her yet. It's pretty bad, really, really bad. You can't just like go in that water because it's very dangerous. Like, because it's full of all the chemicals that come off the road and runoff and sewage and goodness knows what else. Yeah.
Did you hear about the air quality warning?
Oh, yes, I sure did.
It's a giant chemical fire.
Giant chemical fire. Yeah.
What?
This was a weekend for Atlanta. Actually, I saw a very funny picture yesterday. Somebody had taken AI and they made a picture and it was the Atlanta skyline with the interstate running in, and there was like a tidal wave coming up one side. There was Godzilla. There was an AT-AT from Star Wars. There was the Death Star in the background. And it was like, this is Atlanta right now because the sewer, there was a water main break or something, and then a gas main break, and then the chemical fire, and then the hurricane, and another hurricane brewing. And then there's a strike in the ports. The workers that work the ports along the ocean for shipping are on strike now. So it's like, yeah.
Are you going to try to help those friends and get them more food and dog food, or are they gonna have to turn to cannibalism to survive?
Hopefully no cannibalism, that would be really terrible, but yeah, it's rough, man, and there's nothing we can directly do right now because we can't get to them. So what we do is we tend to give to Episcopal Relief and Development, which is, an organization that'll get people in there. We have a really good friend, one of our very best friends, works for the Red Cross. So she was talking to us on Sunday and she was like, all the stuff you've seen on the news, it's worse than that. She's like, there are entire towns that are just completely gone, the whole town. And she said that she actually works in donations. That's her job. She collects money for the Red Cross. So she was calling donors, like repeat donors, and saying, hey, this is Jen with the Red Cross. I'm trying to get some money for this, blah, blah, blah. And she called this one donor and they're like, we can help. We can give you $300. And she said she's never done this before, but she said to them, no, I'm sorry. I can't take it. It's not enough. And I know you can give me more. So that's crazy right there. Yeah.
My great uncle lived he lives in the path. That was in the path of the hurricane.
Mm-hmm.
He lived in that path.
Is he okay?
Yes, they evacuated to Georgia.
Good. Everybody else is okay? Everybody?
I live on a giant hill.
Yeah.
We got was bad rain and cloudy weather.
We got very good flooding of the river, probably the worst flooding we've seen of the river, but it's never gonna come all the way up here, so we're good. But Jason did go down there and get video of it spilling his banks, and then they put the video on the news, which was amusing. So, yeah, they did. I have a friend who is friends with Caitlin Ross, who's one of the 11 Alive news reporters. She does like the human interest stories and stuff. So Jason had posted his video of the river. He went down there with like a giant, he's got an extendable pole, like a selfie stick, and put it out over the river with a GoPro and got video. And then he shared it to his Instagram, and my friend saw it, and she's like, I sent this to Caitlin Ross and she wants to use it. So then he emailed her, so then they emailed back and forth, and then his video of the river was on the news, and we all laughed. We thought it was funny. Okay, so let's do metals, non-metals, and metalloids. All righty, let's see. Everybody get your binders out. Be sure you're ready to go. So the first question is about metals can be hammered. What is the word for something that can be hammered? Do you know, Eunice?
Malleability.
Malleability or malleable. Yep, there's that word. It's a weird word, right? Malleable. Yeah, malleable. So something that's malleable can be hammered. And we use the word malleable figuratively in the English language too. A person that's not, maybe doesn't have the strongest character or convictions and can easily be manipulated or convinced to do things, we call those people malleable. You ever heard anybody called malleable? You might hear that. So yeah, there are some people that are very malleable. They're followers, not leaders. They tend to, yeah.
The next word is probably ductile.
There you go. Okay, so metals are ductile, which means they can be pulled into a wire. All right, we've seen plenty of wires made of metal, right? Have you ever seen a wire made of wood? No. How about stone? No. Yes. So that means those things are not ductile, but metal is ductile. Yes, Miss Lucy.
The lab 7 is a Chris.
Oh, it's not? What's it say?
Mendeleev. Yeah.
That's how it's spelled, with 2 E's.
What? No,
Yeah.
Mendeleev.
Yep. There's 2 E's in his name.
It's Mendeleev.
Mendeleev.
It's
E-E-V.
missing in V.
Oh, there's no V?
Yeah.
Oh, no V. Oh, okay.
Yeah.
Write it down. Or
Yeah,
did you already write it down? Okay. It's weird because there's 2 E's. It looks like Mendeleev, but it's Mendeleev. Yeah. Okay. Anyway. All right. Good. No V. All right. So let's go back to this. Metals are good conductors of what? What are they good conductors of? You both went before. Anybody else know? One of you 3 girls over there want to give it a guess? Good conductors of what? Don't know? Don't know?
It's easy.
All right. We'll bounce back to Eunice. What is it?
Heat or electricity.
Heat and electricity. Okay. Now, metals are not, like we said before, it's harder to find other things pulled into a wire, but we can find other things that are good conductors of heat and electricity. Pure water is a terrible conductor of electricity, but as we'll see in next week's lab, if you add some ions to that water, it becomes a really good conductor of electricity. Glass can be a good conductor of heat, right? You can touch glass and feel it move. Some things that are not good conductors, what's the opposite? What do you call something that's not a good conductor? Do you know? It's not happened yet. You'll know. I'll tell you. It's just October 1st. We still have 30 more days. You'll know. I'll tell you. You'll know. Yeah.
I think it was the opposite of semiconductor or something like that. Or like
Sorta.
it's not a semiconductor.
So here's a hint. Wires, metal wires conduct electricity, and you often find plastic wrapped around those wires. Like right here, you can, I got it on the back here. I got all these things plugged in. If it's not a conductor, it's an insulator, okay? And do you see that up there? That glass thing right there
Yeah.
on that piece of wood? So do you know what that is? Anybody know what that is?
Insulator?
That's an insulator that used to be used when they had telegraph wires. And that was how we would run communication. They would wrap the wires up in there, and that was a way like to connect one wire to another, but keep it contained within that space. So I have a lot of old stuff. You know what? You could start a game and try and guess what the oldest thing in the house is. It'll be
This house
interesting.
is older.
This house isn't that old. It's 1998, but there's something in here that, I mean, I have lots of things in here that are like less than 100 and over 100 years old, but I have one thing in here that's really old. So,
Yes.
no, definitely not that, though that is easily 100 years old. But there's some that are for sure more than that. All right, so how about this next one? Metals are what? What means they're shiny? All right, Emerson. Lustrous, right? They have luster, or they are lustrous, which means that you can polish them and they're shiny. Now, not all metals are shiny. Some metals they start out kind of dull, right? But if you polish them, that's when you get your shine, right? Anybody ever had to polish silver before?
I coin clean.
Yeah, so in my dining room, on top of my china cabinet in there, I have a silver tea service, right? It's got a coffee pot and a teapot and a sugar bowl and a little pitcher for creamer. And it's sterling silver and it's plated. So it's got some other metal underneath, but it's got sterling silver on the outside. Silver will react with oxygen in the air and it'll tarnish. So it turns this kind of blackish color and it loses its shine. And you have to polish it to make it shiny again. So if you look at it in there, like if you see it later today, you'll see it's kind of like a yellowy, gray, weird, ugly color because I haven't polished it in a while, right? So yes, if you polish metal, it gets shiny. Same thing's true of coins. You ever taken an eraser and rubbed it on a coin that looks dirty? You can make that coin look brand new. All right, so what are metals at room temperature? Yeah.
Always.
Are always at room temperature? No, because you can move it. Think about it. You could take a metal and put it in the freezer. Is it at room temperature? No, but what are they at room temperature? This is a state of matter, a phase. What do you think? Look around at all the metals in here. What phase are, oh, no, yeah, solid. Sorry, I got tickled. So except mercury and kind of gallium. Okay, mercury used to be in thermometers and things like that because it's a liquid metal and it expands rapidly when it's warmed up. And they also have they used to do, I've got some in here. So if you ever see old glass that looks like this, kind of silver on the inside, it's called mercury glass. They don't actually use mercury for this anymore. They use like a paint, but they used to put mercury on the inside of the glass and it would give it this really pretty, it was like a mercury vapor that they did it with so that you didn't have like liquid metal dripping off. But mercury is toxic, really toxic. Like you don't want to play with mercury.
Like there's this kind of thing, like there's this kind of like liquid thingy where you put it on a computer and when you like it becomes into like it crushes
like with crystal? Is that what you mean? Yeah, that's yeah.
Yeah.
So mercury, we don't use it as much in anymore in consumer products because like if you had an old thermometer and it broke and you got mercury everywhere, that was bad because it's toxic. Gallium technically isn't liquid at room temperature because we consider room temperature like about 70 degrees Celsius, 23 degrees Celsius, 70 degrees Fahrenheit, and it has to be warmer. I mean, just a hair warmer. But for your purpose, it pretty much is liquid. And I actually have some gallium upstairs, and it's in a little syringe because you can actually move it around. And I might bring it down during lab if we have time and let everybody have a look at it because it's really kind of weird. All right. So metals,
metal on your
a little bit, but not much. And gallium is not toxic. It won't hurt you. Yes, Annabelle.
Mercury is also a planet and
yes,
it was named after a Roman god.
Yes, very good. Yep. All right. What are those are the physical properties of metal. So what are the chemical properties? The ease and speed with which a metal reacts with other elements is known as its what? Lucy? You know?
conductivity.
Not conductivity, but you're close. It ends in ivity. You know?
Reactivity.
Reactivity. Okay. So reactivity. All right. So, and that's not just true for metals. The ease and speed with which any substance reacts with another substance is its reactivity. Okay. The chemical fire in Conyers right now, right? Everybody's seen this, right? This is craziness.
Yes, it woke me up in the middle of the night because of an alert.
Uh-huh. One of the problems with the fire is that they have a sprinkler system because all commercial buildings have to have one. And at some point, the sprinklers went off. And the sprinklers threw water down into the building. And there are some chemicals that react when they come in contact with water. And one of them is sodium. And here's what's crazy. What's table salt made of?
NaCl.
NaCl, sodium
And
and chlorine,
Chlorine.
right? Sodium and chlorine is what make up table salt that you eat probably every day, right? Make some scrambled eggs, yum. Even if it's not in scrambled eggs, it's probably in something else you're making. Chlorine, as it's by itself as a gas, very toxic, not good for you. That's the problem with the fire right now, right? Like there's definitely some chlorine issues, all right? Not good. Chlorine vapor, chlorine gas, not good. Sodium, pure sodium on its own has to be stored in oil because if you let it come in contact with water, it literally explodes, catches fire and explodes. So that's part of the problem with the fire is you've got sodium now that's exploding and catching fire. So, because it's water reactive. They said some of the chemicals were water reactive. So everybody immediately assumed sodium. I'm assuming sodium because it's pretty common. So craziness, sodium and chlorine on their own by themselves are real dangerous, but together, table salt, you eat it every day.
But when you eat too much salt.
Yeah, that causes your blood pressure to go up. All right, so deterioration, let's just say due to a chemical reaction is known as what, Annabelle?
Conductivity.
Not conductivity.
Corrosion.
Yeah, you can say corrosion. So deterioration due to a chemical reaction. So batteries will leak battery acid sometimes in your toys if you don't change them. Like the battery kind of dies or you forget about it. And you leave it, well, it leaks all that stuff out and then it like destroys all the metal parts and then the toy's no good anymore. That's corrosion, right? And also, sometimes you can use corrosion to your advantage. So there is carbonic acid in soda. So sometimes.
I was talking about this the other day.
Oh yeah, what'd he say?
He drinks a drink that has the acid in.
Mm-hmm. Yeah. So carbonic acid is in soda. So even if you're drinking a soda, okay, so you drink a soda, it's a diet soda, you're not putting sugar on your teeth, but you're still putting acid on your teeth. But some people used to use Coca-Cola and they pour it over their car batteries when the terminals would get all yucky, because sometimes the terminals get like the battery acid will come out and it builds up and it makes like this corrosive mess. And you can actually pour Coke on it and it cleans it off. Yeah.
Does that still work to this day?
You can do that. Yep. Coke, Coke has, the acid's a weak acid as far as acids go, but if you leave a weak acid on anything long enough, if it's able to react, you'll see it. All right, so these are some of your answers. So what physical properties are shared by most metals? Lucy?
Luster, malleability, ductility, and conductivity.
There you go. So most metals are shiny, so that's lustrous, malleable, ductile, solid at room temperature, and good conductors of heat and electricity. So sodium and calcium are in different families of metals. Name the families in which they belong and describe the family's characteristics. All right, can you give me sodium, Annabelle?
Metal.
Mm-hmm. It's a metal.
An alkali is a metal.
There you go. Uh-huh. And what characteristics does it have? You know? Do you know?
Sodium belongs to the alkali metals. The alkali metals have only one valence electron, making them highly reactive.
There you go. One valence electron and highly reactive. All right. And Lucy, how about calcium?
Is an alkali earth metal.
Okay. Yep. Right next door. Uh-huh. And do we know anything about them? What do you say?
It has two valence electrons, making them less reactive.
Great.
Than alkali metals.
Right. There you go. All right. So sodium family, alkali metals are soft, shiny, reactive, always found combined in nature, meaning you don't usually find sodium all by itself in nature. Why not? What did I just tell you sodium does if it's left by itself?
Reactive.
Reacts with water. Is there water in the air? Yeah, so that would be not so great. So pure sodium, you're not going to find by itself. You're always going to find it combined with something else. True of all of those alkali metals there. And then the alkali earth metals, that's calcium, right? So it's fairly hard. It's silvery white, good conductors, less reactive, but also always found combined in nature. Typically, you're gonna find those combined and not on their own.
Like here?
Iron is over, where's iron? Iron's over here.
Why
So,
is it Fe?
that comes from its Latin name, that's why. Yep. Have you ever seen, sometimes people will write Female, Iron Man, but they say like Iron Woman instead. That one makes me laugh. Anyway, because it spells female, Female. I've seen that, yeah. So these guys over here and these guys over here are a little similar, but they're a little different too, right? These guys are gonna be less reactive than those. Remember, it's also said sodium is soft. Sodium you can cut with a butter knife, pure sodium. You can just cut it. It's very, very, yep. Yep. All right. What would a metal in group 13, would a metal in group 13 be more or less reactive than a metal in group 1? Everly.
It would be less because group 1 is the most reactive.
There you go. Yes, very good. So group 13 is less reactive than group 1. So reactivity is going to decrease in general from left to right. So we're going to be most reactive here and least reactive here. Okay. These guys here, actually, they're kind of an exception. These guys are pretty reactive right there.
Halogens.
Yeah, the halogens. Right. All right. So how about in what periods are lanthanides and actinides? And where are they placed on the periodic table and why? Lucy, you go.
At the bottom of the last two.
All right. And why are they down there like that? Do you know, Emerson?
So it doesn't make it too long.
Yeah, there you go. Yeah. So lanthanides are period 6, actinides are period 7, and they're grouped together beneath the table to make the table more compact. So they actually fit right here, right? Lanthanides and actinides. But there is a way that you can, if you really need to help kind of visualize it, you can go online on YouTube and find videos of this. But there's a way to create a periodic table that's more accurate, because when you think about it, this pattern repeats, like after neon, the next thing is sodium, right? So it's actually a cylinder. We lay it out flat, but it's actually a cylinder. And there's a way to do it where you can add those rows in and kind of see how it works. It's like origami. It's kind of not my thing, but if it's your thing, cool to look up. Okay. The reaction of a metal with oxygen to form rust. Okay, Everly, what is it? It is oxidation. It's also corrosion. So it is corrosion, and the type of corrosion, the type of reaction that's causing the corrosion is oxidation. So either of those answers would be correct. So you could do either one. All right, how about you? A material that is blank can be hammered into thin sheets, Lucy. Malleable. Weird word, yes. Okay, I know. You got it though. Malleable. Yep, you can hammer it into a sheet. Is aluminum malleable?
Aluminum, yep.
How do you know?
Because it can be hammered into thin sheets. I can break it with my bare hand.
Yeah, can you take aluminum foil and just kind of tear it apart even because you can make it so thin?
Yeah.
Anybody ever seen the Gold Dome in Atlanta? It's our Capitol building for the state of Georgia. Have you seen it?
No.
It's a big building with a big dome on top, and the dome is gold and beautiful. Do you know what's on the dome that makes it gold?
Aluminum?
Gold. It's actual gold.
It's real gold?
It's gold sheet that has been harvested from up here in Dahlonega, taken down there and hammered out so thin. You ever seen anybody use gold foil on crafts or on, like, I use it on cakes? Because small amounts of gold, very small amounts of gold are safe to eat. So I sometimes use it on cakes, and I put little bits of gold. It's so thin that you have to pick it up with a brush and tap it to the cake. Like if you breathe on it, it'll blow away. It's so thin. It's crazy how thin it's hammered out.
I've
All
seen
right.
people put it on slime and the
On slime.
too.
Yep. All right. The ability to transmit heat or electricity is called, what is that, Emerson? Conductivity. Very good. A material that is what can be drawn into a wire, Everly? Ductile. And the ease and speed with which an element combines with others is, Annabelle? Number 9.
Reactivity.
There you go, reactivity. Excellent. All right. Now, let's look at some physical properties of the nonmetals. I don't know why put these guys in little feather outfits, but it was so cute I had to include them because he just looks like he is going out for a night on the town in Featherville. I don't know.
No, he looks like he's going to Mardi Gras.
Yeah, there you go. Yeah, and his tie's funny. It's kind of like they couldn't decide whether to give him a bow tie or a long tie, so they gave him sort of like a, I don't know, a hybrid ascot. I'm not sure what that is, but it's amusing to me. I guess if it were much longer, he would step on it
He just needs a mask.
because he's a little dude.
He just needs a mask and he'll be Mardi Gras.
That's right. So most nonmetals are blank conductors of heat and electricity. What do you think, Annabelle? Poor conductors. That's right. Most nonmetals. So some are not too bad. Some can conduct some, but metals are really what we want if we're trying to intentionally conduct heat and electricity. Solid nonmetals tend to be dull and yes.
Dull and one second. I just forgot it.
You good?
Brittle.
Dull and brittle.
Brittle. Okay, so great example of a solid non-metal. Okay, so who can give me one? Who can think of a solid non-metal? What do you think?
A wooden cube.
Yeah, that's non-metal. That's gonna be a compound. Yep, and those are supposed to be a little more flexible. But yeah. You can also think about things like beryllium, for example. Well, that's a metal. That's a metal in something. Certain compounds composed of metals and other things can become brittle. Ionic compounds in particular, which we're going to be talking about, which is a metal with a non-metal, are always brittle, and that's kind of like a hallmark of them. Okay, excellent. All right, let's have a look at the next slide. Woo! He's got funky hair. Look at it. Metalloids. Okay, where are the metalloids here? They're right here, right? Where do you find these? Where do we use them? Does anybody know where we use metalloids? We use metalloids as semiconductors. All right, so semiconductors are really important in our electronic devices. Basically, they allow some conduction of electricity, but not full conduction of electricity, which helps when you're trying to control how much juice something's getting. And if you've ever, opened up an electronic device and you see these little bit like pills?
Is it resistance?
Yeah, resistors. Yeah, resistors can be in there. Yeah, you can see resistors, and then there are sometimes little semiconductors and all kinds of things in there. And that's where you would find them inside of something like that.
To control like how fast.
Controlling the flow, the voltage. Yeah, how fast it's flowing and how much is flowing.
What do you call a magic dog?
What?
A labracadabra door.
That's a good one. All right, and what are they at room temperature? Metalloids, do you know?
They are.
So they're solid at room temperature. They're brittle, they're hard, and they're also somewhat reactive. Somewhat reactive. All right. Now, what property of nonmetals is the opposite of malleable and
Brittle?
ductile? What do I call you? But yeah, brittle. What does it mean to be brittle? Somebody define that. Lucy, what's brittle? How would you describe it? Yeah, hard. What's an example of something that's brittle? Can you think of something that's brittle? You?
A rusty coin.
Depends on the coin. These are made of copper, so they're actually pretty flexible. You can bang these into shapes, right?
Right.
So, yeah, you ever do the thing where you run the penny through the machine and it spits it out with a design on it? Most tourist attractions will have that. You like put a penny and a quarter in, it keeps your quarter and it flattens your penny and makes it useless. But it's fun. So brittle means that it's not flexible at all. It's very inflexible. So if you put pressure on it, it will chip and break and fracture. A great example of something that's very brittle.
Is it fracture?
Like break, yeah, fracture. So emeralds. Anybody have an emerald, or anybody's mom have an emerald?
I think I have an emerald like ring somewhere like, in a vault.
Do you have a May birthday?
Yes.
Yep, that's why. So May, the stone for May is an emerald. I got a couple because Drew's birthday's in May, so I have some emeralds because that's, birthstone color.
My dad was born in May, and it's the international one for drums, and he plays drums.
There you go. So I actually inherited a beautiful big emerald ring from my grandmother, And it was getting loose, the prongs were getting loose, so I wanted to take it to a jeweler and have them tightened up. And like 4 or 5 jewelers refused to touch it because emeralds are really brittle and it was an antique and they didn't want to mess it up. They don't want to be responsible for it. So yeah, brittle means it'll fracture really easily. Like glass, we've managed to make glass much more flexible, which is necessary. Like if you tap your glass window, you'll see it kind of whoop, 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 whoop. But glass can also be more brittle if it's not. We learned to treat it to make it more flexible, which is good for our purposes, right? Diamonds are brittle, right? So what happens to atoms what happens to the atoms of most nonmetals when they react with other elements? Okay, Everly?
They share the electron.
Right. So atoms of nonmetals usually gain electrons. Yeah, they can share. Depends on what. Sometimes they're going to share, and sometimes they're going to just steal them. And we'll talk about that when we start talking about ionic and covalent bonds. Yeah, but they usually tend to gain them. All right. So now I know physical properties of nonmetals include, and we did these already, right? Nonmetals are dull, brittle, poor conductors. So a great example of a solid one, if you're looking for a solid nonmetal, right here, carbon is a polyatomic nonmetal. Carbon, you can see carbon in multiple forms. In graphite, pencil lead is not lead, it's carbon. Charcoal, right? And if you compress carbon long enough, what do you get? Hard enough, long enough, hot enough, what does it become? Diamond. Diamond is pure carbon. If you put it under enough heat and pressure, your pencil lead will turn into a diamond. That's what happens. So yeah, brittle, very brittle. It's a great example of a non-metal that's very brittle. All right, and hopefully you don't need extra help with anything. Okay, what are the non-metals in group 16 of the periodic table? All right, Eunice.
Oxygen, sulfur, and selenium.
Yes, oxygen, sulfur, and selenium. These are called diatomic molecules. Oxygen, sulfur, and selenium. What does diatomic mean? So diatomic means they're never by themselves. They're always hanging out with a buddy. You're never going to find oxygen by himself. He's very lonely and insecure. He's never going to be O. He's always going to be O2. He's got to have a buddy. Yeah.
Because like oxygen never is separated.
No, it's never. It's always with somebody else. All right. So how do chemical properties of the halogens compare to the noble gases, Annabelle?
No, there are no metals in the gases. Oh, thank you.
So say it again, sorry.
There are no metals in gases.
Yeah, so the halogens, these guys are real reactive, and these guys don't react with anybody. We call them inert. They're non-reactive. They just chill. They're just chilling. They don't want anything to do with anybody. These guys want to fight with everybody, basically. They either want to like make friends or fight. That's all they want to do. Like
7, 8, not 7, 8.
7, 8.
Yeah.
Nitrogen and oxygen?
Yeah.
Well, you get less reactive as you go this way, right? Until you get to here, and then you're real reactive. So, all right. So, how is the periodic table organized? So, this is a big open-ended question. What you get, Eunice?
They're organized by increasing atomic numbers or increasing protons.
Right. So,
Like
so increasing atomic number. And they're arranged into rows called periods, columns called groups. Elements in the same group have similar properties. So your periods go this way, right? And your rows go, and your groups go this way. And everything in a group is similar. So these guys are similar, these guys are similar, right?
What about the nitrogen and oxygen? Why are they in diatomic nonmetal?
Well, because they're always together, right? They always have two that are together.
Oh.
There you go. All right. And lastly, I know that families containing nonmetals include what, Annabelle?
Carbons, nitrogens, oxygens, halogens, noble gases, and hydrogen.
There you go. Yep. I didn't put that answer there, but you're right. All right. Ionization energy. All right. Ionization energy, electronegativity, and electron affinity. They do what as you move across a period? Periods go this way. What do these things do? Do we know? So if we look at the graph, look at that graphic here. Electron affinity is going to increase as you move across a period. Electronegativity is going to increase. and ionization energy is going to increase. And you know that because the arrow's moving that way. So it shows you that as you go from left to right, those things are going to increase as you move across a period. And what's going to happen as you go down a group?
It decreases.
They're going to decrease. So you can see that right there, right? So electronegativity, electron affinity, ionization energy, and we're going to talk more about these things, okay? But these are the things, these are the characteristics that impact how these elements are going to react with other elements. So based on that, you would expect to see something really electronegative with high ionization energy and high electron affinity, right? There, right? And you do. All right, atomic radius. How big is this atom? Radius being from the center out, right? You know what a radius is from a circle, it's from the center to the edge. So atomic radius and ionic size. What do they do as you move across a period? So across from left to right, what happens to those things? You know? They're going to decrease as you move across a period. And they're going to increase as you move down a group. Here's why. Okay? Think about this. So you've got these guys over here that wait, I'll come back to it when we have a better understanding of it. I'm going to get you confused if I say it now. We'll come back to that because we're going to go over it and over it again and again. Looking at this, melting points and boiling points pass through two cycles. You may not know all these. I'm just kind of giving you a heads up of these, of increasing, peaking, and decreasing as you move across. So all of these things, these characteristics, there are patterns. That's what I'm wanting you to see, is that there are patterns in the table when it comes to these characteristics. So here's your table in general. You have your main group elements, right? And within them, you've got this alkali metals over here, which we already looked at. Then you have your alkali earth metals. Then you have your halogens, right? And your noble gases. And then this guy, what's with hydrogen? What's he part of?
He's part of the.
He's diatomic, but really the thing with hydrogen is he's all by himself. He really is. All right, so let's watch this real quick. We have a quick Professor Dave that gives us a tour of the periodic table.
Professor Dave, explain.
Yep. And we're going to have more ads because we can't get away from him till this thing is over, and I cannot wait because it never used to put ads if I was doing them in the show.
Tired of voting at.
Me too.
Pretty much everyone knows what this.
Gonna run to the back. You
Even if you don't know much about it. It's the periodic table of the elements, which at first seems like a random arrangement of substances, most of which sound strange and foreign. But the way the elements are arranged reveals many beautiful patterns that tell us about how nature operates. In the mid-1800s, lots of chemists were trying to come up with a way to depict all the elements in table form, and many different formats were proposed. But it was the one by Dmitry Mendeleev that stuck, because of how well it correlates data, as well as its predictive powers. He arranged the elements into rows called periods, and columns called groups. Elements that had similar behavior were put in groups together, which helped to correlate existing data. And it also predicted the existence of elements that had never been seen before. With the gaps in the table, Mendeleev said there must be elements that go in these spots, and he predicted some of their properties. Eventually, these elements were discovered with the properties precisely as expected. And now we have all the metals, metalloids, and nonmetals organized nicely. It wasn't known at the time, but the reason elements in the same group behave similarly is because they have the same number of valence electrons. Look at group 1, for example. These elements all have one valence electron, or one electron in their outermost shell. As you go down the table and n increases, you gain a shell each time, but whichever is the outermost shell, there is only one electron in it. Every element in group 2 has 2 electrons in its outermost shell, and so forth. This simple fact determines many characteristics about each element, in ways we will continue to see as we learn more chemistry. There are some periodic trends that we can recognize when we look at the table. The first one is atomic radius, or the size of the atom. As we proceed downwards on the table, atomic size increases because we add shells. As we go to the right, atomic radius decreases because we are moving within a shell, and each element to the right has one more proton in the nucleus
Now
than the
he's
left.
explaining what I
So
said I
there is
do.
a stronger electromagnetic attraction felt by the electrons, and the radius shrinks. That means overall, atomic radius increases going this way on the periodic table. Ionic radius is a little different. Electrons repel each other, so adding an electron makes an atom bigger. Taking one away makes it smaller. Ions with the same electron configuration will have their radii decrease as the atomic number increases. Next, we look at ionization energy. This is the energy required to remove an electron from the atom. It will always be an electron in the outermost shell. The electromagnetic force that attracts the electrons to the protons drops off very quickly with distance. So the farther away an electron is from the nucleus, the easier it is to pull it away. This means the ionization energy trend is precisely the opposite of the atomic radius trend. Francium, a very large atom with only one valence electron, will be easy to ionize because the electron is so far away from the nucleus, and atoms like to have their outermost shell completely full. Losing the electron means this shell is gone, and the one below is completely full, so elements in group 1 will easily lose one electron. Looking at the opposite corner with helium, there is only one shell, so the electrons are very close to the nucleus, and the shell is full, so it is very stable. For this reason, it requires much more energy to ionize helium. So the ionization energy increases going this way on the periodic table. Elements can have successive ionization energies for removing more than one electron. A second ionization energy will always be greater than the first and continue to increase from there, since the more electrons you remove, the less stable the atom becomes. An element will have a huge jump in ionization energy after you take the last one in a shell, because then you jump to the noble gas electron configuration from the previous shell, which is full, so it really won't want to give up any more electrons. There are just a couple exceptions to the ionization energy trend, but we can rationalize them. Look, for example, at the second row. From lithium to neon, the ionization energy should increase each time we add a proton to the nucleus and the radius contracts a little. But something like oxygen, which dips downwards from nitrogen's ionization energy, does so because of orbital symmetry. Here is nitrogen's orbital diagram, as well as oxygen's. Notice that nitrogen's 2p orbitals are precisely half full. This gives nitrogen a special stability, just like elements that have a full outermost shell. If nitrogen loses an electron, it loses that special stability. But if oxygen loses
So I'm gonna pause him here, because
an electron,
it's kind of just extra for you guys. And you're gonna, we're out of time. You can watch it later if you want to watch the rest of it, because most of it's just, that's just extra for you guys. So couple quick messages. That's why it's important that we do this before we wrap up. Heads up, Q2 is fast approaching. Q2 is gonna start with lesson 10. This means that if you owe me work, you need to get me that work. Check your syllabus. It's going to be the Monday before Q2, so it's October 20. And I'm gonna need your work. If you owe me something and you haven't given it to me, that's gonna be a 0, right? You're gonna get a progress report, so you wanna get that right. All right, so heads up, Q2 is fast approaching. Also, I just wanted to send a personal invitation. Drew and I are organizing a trunk or treat at our church on the 26th. If you like to trick or treat, come join us. It will be fun.
I'm going to my local brew fest.
Oh, yeah?
Local brew fest.
Well, this is gonna be from like 5 to 5:45. It'll be real fast. So if you wanna come grab some candy, come ahead. And last thing, unit test 3. Unit 3 was quick, wasn't it? It was 2 whole lessons. There was unit 3. So because unit 3 is now done, we will be wrapping it up with our test, and the following are the topics you need to know. Remember, this will be saved, right? Where do you find these? Where do you?
Student Dropbox.
Yes, in your Dropbox. You know what to study, right? So keep it together and you know what to study, and you'll be good to go. And always, always, always be watching your messages and everything else for your Tinker Day announcement. Whenever it comes, I've got our donuts. We're ready to go.
I hope it's on a class.
And also, ladies, should you be interested, I am hosting one of 2 Atlanta area Tinker Day parties, official from the school, from Hollins. And I'm hosting it this Friday night at 7 p.m. Ladies, if you wish to come, you're welcome. Sorry, dudes, we don't take dudes. So there you, it's a women's college, so yeah. Sorry, dudes. All right. So there you are for that. You guys can go ahead and get yourselves situated for lab. Yeah, this is a kind of a easier, it's a pencil lab today. Mm-hmm.